In this paper, we delve into the properties of vortices as systems specific to the acoustic world, employing both hydrodynamic theory and the corresponding hydrodynamic Maxwell equations. We first define and classify vortices, identifying two primary types, the rigid body vortex and the irrotational vortex. The rigid body vortex is characterized by a constant angular velocity that does not depend on position, while the irrotational vortex exhibits fluid velocity decreasing inversely proportional to the distance from the axis. We also discuss the core vortex model, which combines elements of both rigid body and irrotational vortices. This model, developed by William John McWarren Rankin, features a core that rotates as a rigid body with an angular velocity, and its fluid velocity follows the rigid body vortex equation for distances within the core radius. For larger distances, the vortex behaves as an irrotational vortex with zero vorticity, and its fluid velocity is described by the irrotational vortex equation. Furthermore, we touch upon other types of vortices, such as the spherical vortex, ring vortex, Berger's vortex, and the Lambosine vortex, which are detailed in specialized papers. Notably, the theoretical and experimental study of vortices in quantum superfluids and superconductors holds particular importance for the modeling of the acoustic world. The paper then proceeds to utilize Maxwell's hydrodynamic equations for the vortex, allowing us to deduce the force between two vortices and obtain the expression for the equivalent mass of the vortex and the permittivity of the electroacoustic field. This leads to the expression for the energy density of the acoustic field, which in turn explains the change in the propagation speed of the acoustic waves and the acoustic lensing property of the vortex. The paper discusses the system of two-point vortices, using complex potentials to analyze their behavior. It begins by introducing the concept of a two-vortex system, where the velocities of the two vortices are determined through equations 7 and 10. This system behaves as a single vortex at distances greater than the distance between their centers, with different scenarios for identical, opposite, or differently oriented vortices. The paper then moves on to discuss hydrodynamic Maxwell equations for the vortex, which were deduced from the analogy between electromagnetism and fluid mechanics. These equations include the continuity equation, 14, the absence of magnetic monopoles, 15, Faraday's law of induction, 16, and Ampere's law with Maxwell's correction, 17. The defining relations for the physical quantities involved are also provided in equation 18. The acoustic charge density and acoustic current density are defined in equations 19 and 20, respectively. The energy densities are given in equation 21, written in both Gaussian and MKSA systems of units. The paper considers a vortex with a core and an ideal fluid with zero viscosity, where the velocities within the nucleus of radius d are independent of time according to relation 2. In summary, this section of the paper presents a comprehensive analysis of the two-vortex system, including its behavior and hydrodynamic properties. It uses complex potentials to derive velocities and introduces the hydrodynamic Maxwell equations, which are fundamental in understanding the behavior of vortices in fluid mechanics. The paper also discusses the energy densities and considers a vortex with a core, providing a detailed framework for understanding vortex dynamics in ideal fluids. In the context of fluid dynamics, this research explores the behavior of vortices in a fluid with periodic motion. The authors introduce the concept of an acoustic vortex, which is a vortex that behaves as an acoustic dipole with cylindrical symmetry. The acoustic charge and current densities are defined, leading to expressions for the electroacoustic field vectors inside and outside the vortex core. These expressions reveal that the force between two vortices is attractive due to the magnetic acoustic component being twice as large as the electrical component. The paper then delves into the case where the distance between two vortices is much greater than the diameter of the vortex core. Here, the charge of the vortex that generates the electroacoustic field is calculated, resulting in a total charge for a sample vortex placed outside another identical vortex. This charge is used to determine the intensity of the electroacoustic field, and subsequently, the force between two vortices. This force is found to be an acoustic dipole force, analogous to the electrostatic dipole force. The authors also discuss the Newtonian interaction force per unit length, which requires multiplication by a constant to obtain the equivalent mass of the vortex. This constant is determined to be of the same magnitude as in the case of the interior of the vortex core. Furthermore, the acoustic charge in the Gaussian system is calculated, and the equivalent mass of the vortex is found to be the mass of the vortex core. Finally, the paper draws an analogy with the Maxwell equations for an oscillating bubble behaving as an acoustic monopole with spherical symmetry. The constant is expressible as a function of the acoustic permittivity for the vortex, which depends on the parameters of the fluid, including its undisturbed density and periodic motion. The acoustic permeability is also defined, completing the comprehensive analysis of the acoustic vortex in the context of fluid dynamics. The paper discusses the hydrodynamic and acoustic properties of vortices in compressible fluids, focusing on the concept of acoustic permittivity. It begins by introducing the Newtonian force per unit length in the MKSA/SI system, which is proportional to the mass of the vortex core. The energy densities of the vortex field are also explored, with expressions for both the kinetic energy density and the relativistic acoustic energy density inside and outside the vortex core. In the context of a universe model, the gravitational charge density is equivalent to the mass density, and the gravitational field strength follows a similar Maxwell equation as the hydrodynamic field. The paper highlights the role of the background field in generating interactions between systems in the acoustic world, leading to the derivation of hydrodynamic Maxwell equations. The vortex is then considered as an acoustic lens, with the velocity field generating density and pressure variations that modify the propagation speed of acoustic waves. This results in a refractive index for the fluid in the presence of a vortex. Two expressions for the index of refraction are provided, with the second expression differing from the first by the second power of the ratio of the fluid velocity to the vortex velocity. A better approximation of the refractive index expression is proposed by averaging the two equations. The paper demonstrates the existence of acoustic permittivity and its relationship to the mass of the vortex core, as well as the energy densities within and outside the vortex core. It also establishes the vortex as an acoustic lens, influencing the propagation of acoustic waves through variations in density and pressure. The connection between the hydrodynamic field and the gravitational field is discussed, and the importance of the background field in generating interactions between systems in the acoustic world is emphasized. In this paper, we have demonstrated that a vortex, as a system with internal angular momentum, behaves like an acoustic dipole when interacting with other vortices at distances greater than the core radius. The hydrodynamic equations for the vortex show an acoustic permittivity dependent on the undisturbed fluid density and angular velocity, highlighting the role of fluid periodic properties in generating interactions specific to acoustic waves. These periodic properties explain boundary conditions imposed by quantification of characteristic properties of systems specific to acoustic waves and, by analogy, to the electromagnetic world. We have also shown that the energy density of the electric acoustic field of the vortex core is the rotational kinetic energy density, and the energy density of the magnetic component is proportional to the fluid pressure. Since the vortex induces changes in fluid density and pressure, and therefore in the propagation speed of acoustic waves, the corresponding acoustic refractive index causes the vortex to behave like an acoustic lens. We evaluated this acoustic refractive index and the possibility of the vortex becoming a dumb hole, allowing us to solve problems such as pulsating vortex under the action of an acoustic wave, multi-vortex system, and pulsating bubble system captured by a vortex. In the context of fluid dynamics and quantum mechanics, this research explores the analogy between electromagnetic and acoustic phenomena. The study focuses on the acoustic world, where oscillating bubbles create vortex rings and clusters, mimicking the behavior of electromagnetic fields and forces. The authors utilize mathematical models, such as the Onsager's reciprocal relations, to describe the interactions within these systems. They also draw parallels with quantum mechanics, particularly in the context of Bose-Einstein condensates and vortex dynamics. The paper discusses the concept of acoustic forces, which are akin to electrostatic forces, and acoustic scattering and absorption cross-sections, similar to their electromagnetic counterparts. It highlights the significance of vortex interactions in both the acoustic and electromagnetic realms, referencing various studies on vortex rings and clusters. The authors emphasize the importance of understanding these interactions for advancing our knowledge of fluid dynamics and quantum mechanics. Furthermore, the paper delves into the realm of gravitoelectromagnetism, a theoretical framework that attempts to unify electromagnetic and gravitational forces. This is achieved through the use of vectorial theories of gravitation, which treat gravity as a vector field rather than a tensor, as in general relativity. The authors cite several works that have explored this idea, including those by Maschhun and Weinberg. In addition, the paper touches upon the concept of time as a cyclic dimension, referencing Dolce's work on canonical quantization and the implications for our understanding of classical cyclic dynamics. This perspective could potentially revolutionize our comprehension of quantum mechanics and the nature of time itself. The research also engages with the idea of a dumb hole, an acoustic equivalent of a black hole, where sound waves are trapped and cannot escape. This concept is explored in the context of oscillating bubble clusters and their ability to create regions of silence. Overall, this study contributes to the ongoing efforts to establish connections between different areas of physics, from fluid dynamics to quantum mechanics and gravitation. By exploring these analogies, researchers can gain new insights into complex phenomena and develop innovative approaches to understanding the fundamental laws of nature.